Sabine Hossenfelder's critique of IBM and Google quantum computers. She argues that the way the achievements are framed is misleading and overhyped. Below is a breakdown of her main concerns, with references. What she does acknowledge, Hossenfelder states that quantum computers work in principle. The physics is understood, and prototypical machines exist. What she questions is the gap between what's claimed in press releases and what's practically achieved, or will be achieved in the foreseeable future. Her main criticisms of quantum computing claims. Here are some of the key points she raises when analyzing announcements from Google, IBM, and the broader quantum computing hype. 1. Scaling and practical usefulness. In a blog post titled "Don't Fall for Quantum Hype," she emphasizes that while quantum computers can in principle provide speed-ups, the real bottleneck is scaling to many reliable qubits and error correction. She warns that the parallel with nuclear fusion is apt. The physics is known, but turning it into a widely usable technology is a long haul. In response to a Google announcement, she remarked, "The problem is that the task given to the computer isn't all that useful. They use this particular problem because it has been formally proven that the calculation is difficult to do on a conventional computer." Her phrasing suggests that while the claimed milestone is real in a narrow sense, it is not yet meaningful for broad, practical computing uses. 2. Hype versus reality. She stresses that there is a lot of omission. Announcements often downplay or ignore the enormous resources, overhead, error rates, classical computing support, and limited kinds of problems that current quantum machines can solve. Example, she points out that the announcement by Google made a strong impression, but the actual problem solved was a very narrow benchmark for random circuit sampling, not a broad application. She says that many articles mislead by mixing up "can do some special problem faster" with "useful for everyday problems," or "just around the corner." 3. Verification and clarity of claims. She highlights that some claims about quantum supremacy or quantum advantage are contested. For instance, in the case of Google's 2019 claim, IBM pushed back, saying a classical computer might do the task faster than Google estimated. Hossenfelder's own commentary on X about Google's 2024 more recent announcement showed she saw significant ambiguity in how the achievement was framed. 4. Economics and resource demands. She emphasizes that even if quantum hardware works, it might not make economic sense unless problems extremely well matched to quantum machines dominate large parts of computing. She writes, "When I ask, does it scale, I am referring to economic limitations." For example, she points out that current quantum machines rely heavily on classical computing for control, error correction, compiling, etc. The quantum part isn't doing everything alone. Why she uses strong language like hype and "don't fall for quantum hype." Because from her vantage point, many announcements sound like we are right at the doorstep of quantum domination, whereas she believes the technological and economic gaps are still large. This creates a risk that resources, public and private, will be channeled into exaggerated expectations rather than grounded milestones and careful development. She sees a pattern: big press releases, big numbers, qubits, years of classical computing time saved. But often the limited applicability and remaining challenges are downplayed. She suggests the public communications from those companies are overly optimistic or misleading, in the sense that they present results as if they are closer to general-purpose quantum computing than they actually are. They emphasize what has been achieved without always making clear what still remains: error rates, scaling, useful applications, etc. That's important because when the public or investors interpret claims too optimistically, they may think a large breakthrough has been achieved, while in her view, the real breakthrough, commercially viable quantum computing, is still distant. Summary of why Sabine is skeptical of Google and IBM's claims. Because the achievements, while real, are narrow and solve special benchmarks, not broad problems. Because the claims are often framed in a way that suggests we are soon there, when she thinks we're still far off in scaling and economics. Because she believes the communication sometimes gives the impression that quantum computing has moved from laboratory research to industrial technology, far more than the facts support. Because she wants more clarity. What is the useful quantum speedup? How many qubits? With what fidelity? How much classical overhead is still needed? What is the cost versus benefit?